one column by 9 by 9, multiplied by 9 by 1. So how do you represent that in a initial notation form? Sigma ij, yeah? So we need to write your stiffness matrix. So this one is, okay, then you have epsilon mn. So this one, dummy indices, you end up with those two free index. I mean, they can be written in different forms.Cijkl and then epsilon kl. Take note, these are dummy indices. As long as you don't repeat an index more than twice in an equation. So as you can see, it's more convenient to write this equation here. And how does this one equate to the one-dimensional equation that we had by using your stress-strain curve? This one is your stress, this one is your modulus, which is the stiffness, and this one is your strain. So just putting things into perspective. So this one initially observed from experiments, and then they blew it up to a more 3D analysis. Okay? So of course you can have this one as a matrix. It's up to you if you want to write this one. Of course we will be able to simplify that later, don't worry. It won't be a 9 by 9 really. We'll definitely end up minimum 6 by 6. Still a lot. But if we're going to apply the different principles of simplification, plane strain theories will end up with a 3 by 3. Getting better, isn't it? Okay, so a lot of assumptions, and we will be looking into that later. So there you go. Just to simplify this one, sigma ij, you write it, but if you put it into an equation, this one is a 9 by 1. And these are the values of your strain. Okay, if you have a Young's modulus or isotropic, as you can say. If you have an isotropic material, then you further simplify this equation. But we'll do that later. This is just showing now. If you have this one here from 3D to 2D, from a 3D to a 2D, then you simplify matters. Okay? Of course, this one is very much applicable in design anyway. So there you go again. Components of your stress tensor. There will be 9 components. You have 3 normal, 6 shear. I repeat, first subscript refers to the direction of the normal, meaning perpendicular to this face that it's acting on. And the second subscript refers to the direction of that stress. Okay? So, components of the stress tensor, you have 2 normal stresses and 6 shear stresses. Later on, we'll have a look at the symmetry or the symmetry of these stresses, wherein sigma ij is equal to sigma gi. Symmetry. That's why sometimes for this analysis, to be able to simplify things, we just use initial notation. Because we probably don't want to be keep on repeating on writing this matrix just to come up with this one. Okay, we probably just use this one and represent it as symmetric rather than writing 2 matrices together, or equating 2 matrices, that is. We will be discussing this one and deriving this one as well. I'm sure you will enjoy the derivation part of this one. Okay. This is just saying a lot of equations there. So we will be going that later. That is. Okay. So as you can see, if you're looking at the stiffness matrix, This one is strain, this one is stress, this one is your 6x6 matrix. Once you apply the principle of symmetry, then you reduce that matrix size of 9x9 to 6x6. So as you can see, this is the simplest form at the moment. So as you can see, on your left side you have a strain, and this one is a stress. If you put stress on one side equal to a stiffness matrix multiplied by your strain, then this matrix here will be complicated. So this is not the stiffness matrix, this is the compliance tensor. So this one is your Young's modulus. If I'm going to have sigma ij equal to Cij KL epsilon KL, if I write this one into matrix, I can have this one as sigma equal to C multiplied by epsilon. Yes? So this one is your stiffness tensor or stiffness matrix. Let's just put there a stiffness matrix or tensor, no problem. Let's do the reverse, wherein we have your strain. Okay. Now I'm going to use another letter here, symbol, Sij KL. Yes, and then we have now here your stress. Dummy index, free index, which is the same as this one here. So this is not called the stiffness matrix, this is now called the compliance tensor. Or compliance matrix. So we're just looking at terms at the moment. We're just trying to define things, making things a bit more interesting. Yeah, just definitions. Yeah. So this one here, again, going back to this one is a dummy index, and then you come up with your free index. So, like I said before, you can even try to have some more understanding on the theory of elasticity. You have to go back a bit and study your tensors, vectors, scalars, and higher order tensors. Yes. So there you go. Epsilon or Eij equal to Sijmn. So this one is dummy, so it doesn't matter. A sigma mn, where this one is your compliance matrix or compliance tensor. This one is your Young's modulus, and G is your modulus of rigidity, which you can simply calculate by knowing your Young's modulus and your Poisson's ratio. So as you can see, we're trying to now to integrate what you have learned in strength of materials, mechanics of materials, your materials courses, and different principles here. This is just another representation. As you can see, this one is the stress, this one is your strain, and this one is your stiffness matrix. And then, of course, you have lambda and 2G. Lambda, or the Lemaitre's constant, is given by this equation here. E, Poisson's ratio. This one is your Young's modulus. CIJMN is your stiffness matrix. So what's the relationship between your stiffness matrix and your compliance tensor? Stiffness matrix is the what? Inverse of your compliance. So why is it, right? Why do they call this one stiffness matrix C, while this one is the compliance? Yeah, stiffness matrix, compliance tensor. And the relationship inverse. Okay? So again, going back, we have 3 normal stresses and 6 shear and so on. Of course, getting more interesting is the okay. Any questions so far? Theory of statics. What do you have with theory of statics? Forces and moments are, the summation of forces, summation of moments acting on a body is equal to 0. Principle of static equilibrium. What about the principle of static equilibrium for this one here? Stresses. Okay? So we don't have a principle of so-called equilibrium wherein we have the sum of the moments, sum of the forces equal to 0. We have the sum of the partial derivatives. Okay? So if you have now this one here, as I said, comma is a differentiation. Let me just copy this one first. So let's write the equilibrium equation. So at the moment, we're just trying to define terms here. So here we have I and J equal to 1 to 3. So let's try to define this one. We're looking at the equilibrium equation. Equilibrium equation. So have a look at this one. We have constitutive equation. So if I'm going to write it, what is our constitutive equation? This is our constitutive equation. So what is this one? Also constitutive equation in 3D. This is also your constitutive equation. So what is a constitutive equation? It defines the behavior of your material. That's a constitutive equation. Now let's look at a equilibrium equation. And how do you write equilibrium equation? Please take note, we're not solving anything, we're just defining terms. We're not solving anything at the moment, but before we solve things, I want you to understand all these definitions. So we're just going through definitions. Now again, the purpose of using indicial notation is to be able to save space. Okay, so let's just try to expand this one. So what if we have I equal to 1, and then J is equal to 1 to 3? So what do we have? Partial differentiation. So we have now this one here. Partial of sigma what? 1, 1 with respect to x1. And then we have a repeated index. So there's a summation. Yes? Yes. Partial sigma 1, 2 with respect to x2. Simple. Partial sigma 1, 3 with respect to x3. This one is equal to 0. Now, if we have I equal to 2, and then for some j 1 to 3, it's the same. So we end up with a partial sigma 2, 1 with respect to x1, partial sigma 2, 2 with respect to x2, partial 2, 3 with respect to x3 equal to 0. And then you do the same. I equal to 3, j equal to 1 to 3. And then you have now partial sigma 3, 1 with respect to x1. So I'm just writing things now. So as you can see, it's just a definition. So instead of writing all of these three, I can simply write them as sigma ij, comma j. So that's the purpose of initial notation. So I hope you understand now why do we have to use initial notation. We're not complicating things. We're just trying to make things simpler for us. But before we can even use this initial notation effectively, we should know its rules. Okay, so we're just trying to learn a new language here. Language of mechanics, that is. Okay? So we have now a equilibrium equation of elasticity. Again, there are definitions on surface tractions or body forces. At the moment, I won't be discussing too much on this one. You can read on this one when I post it there. So as you can see, it's pretty straightforward, but to be able to understand more, let's do some examples in the future. So what's the meaning of this one here? I want to finish this one and then let's go. Okay?
Let me go.
These are definitions that you will need in your design. Believe me, you'll need these stresses in your design. If you're going to do a design, you probably want to understand what principal stresses are. So, we have, so we have 9 stresses. We have 9 stresses, and then we have 3 normal and 6 shear. But if you're going to rotate that element, there will be a point wherein there will be 3 stresses, normal stresses with 0 shear. Okay, so instead of having 3 normal stresses and 6 shear stresses, you would like to rotate this one such that you only have 3 normal stresses, 0 shear stresses. And these stresses are specially called principal stresses. So what do you use in your design? The maximum principal stress. If you are going to design, one of the things that you will need to know is the principal stress. Now this one again will depend if your material is brittle. If your material is brittle, that's why you're taking materials. If your material is brittle, then this one is very much applicable. If your material is ductile, then you need a different set of stresses, that is. Okay, but at the moment, just accept that if you're going to rotate this element, wherein you have 3 normal, and 6 shear, you will be able to rotate it in such a way that there will only be 3 normal stresses, and that these 3 normal stresses are called principal stresses. That's the meaning of this one here. Okay? It's the same with 2D. So if you have 2D, you have 1, 2 normal, and 2 shear. 2 normal, 2 shear. But you will be able to rotate this one such that you only have 2 normal stresses and no shear stress. Principal stress. That's the definition of principal stress. Okay? And initial notation, this is how you write this one here. How do you solve for the principal stresses? This is your equation, which we will do next meeting. Okay? So we have now defined quite a lot of terms. We were able to discuss so many terms. We started from tensors, we went to constitutive equation, we went to stresses, we went to equilibrium equations, and so on. Please remember all of these terms. Okay, let me just summarize. So what did we do today? So we look at tensors. Yes, we look at tensors. Tensors can be scalar, say a temperature. We also look at vectors, can be forces. And we also look at higher order rank tensors. In this case, what is really important to us will be your stress, which is a second order tensor, and then you have your strain. We've also discussed a fourth order rank tensor, which is your stiffness matrix, and then your compliance matrix, wherein we know that, let me write it in a matrix form. This one is the inverse of that. So that's tensor, right? We also look into our constitutive equation. So what is this constitutive equation? Constitutive equation defines the behavior of your material. From our stress strain curve, we were able to define that your stress is equal to the modulus multiplied by your strain. If we blow this one up on a 3D scale, then we're looking at sigma ij equal to Cij mn epsilon mn. That's your constitutive equation. Another definition that we had will be your equilibrium equations. Yes? So this equilibrium equation, to make it simple, sigma ij, this is comma j. This one is equal to 0. That's your equilibrium equation. Comma meaning differentiation. Of course, we have discussed that instead of writing the whole matrix here, it makes more easy or easier to write it in initial form. The same is true with this one here. Okay? And then what else did we discuss? So what about your stress components? So you have 3 normal stresses, and then you have 6 if you rotate it, okay, if you're going to rotate that element, you probably will be able to get 3 normal stress components or stresses, which is the principal stresses, which are the principal stresses. Okay, and then we have your, so what are your normal stresses? This one is sigma 1, 1, sigma 2, 2, sigma 3, 3, and this of course 1, 2, 1, 3, 2, 1, 2, 3, 3, 2, 3, 1. Yeah? And then you have your principal stresses. So this one will be sigma 1, sigma 2, and sigma 3. Of course, this one is looking at a 3-dimensional point of view. We can always simplify this one to 2-dimensional analysis, wherein instead of sigma 1, sigma 2, sigma 3, we can reduce this one further to sigma 1 and sigma 2. So at the moment, we didn't solve any problems, we just learned the definitions. So this is a new language that we're learning at the moment. Okay, the language of mechanics. Right? Questions, anyone? So I'll see you next week. We won't be able to meet on Thursday, so I'll see you Monday. I will make an announcement which room, if we're going to use this room, we're going to bring it.